So in the previous video we had discussed about infiltration and how infiltration plays a predominant role in defining the runoff, and also we had discussed about what is the way in which we try to determine the infiltration. There are other processes in of infiltration that we need to study. Okay, how to estimate the infiltration, how to analyze the infiltration. We will do all that later, but before that what I'll do is I have left out a small bit in evapotranspiration. I had given you explanation of what is evapotranspiration, and I told you that there is a method through which we can determine the evapotranspiration. Okay, so what we'll do is we'll quickly look into the evapotranspiration and a method to evaluate the evapotranspiration. Okay, so as you can see in the screen, you can find out that there is a method that I'm going to explain, which is called as Brandy-Cuddle formula. Okay, so using this equation we could be able to solve the evapotranspiration from any given area. Okay, so basically evapotranspiration is applied for a farmland or any vegetative area. Okay, wherever there is a vegetation we can determine the evapotranspiration from there. Okay, I told you what evapotranspiration basically means. Evaporation that is taking place from the soil and the and also the water that is consumed by the plants through a process called transpiration. If they are combined together, we call it as evapotranspiration. So again, this is an empirical formula similar to that of Mears formula, Rover's formula. So in this case, what we need to focus upon is the equation. Okay, the equation that is given to you is et is equals to 2.54 k into f. Okay, k is the crop factor. Okay, based on the type of crop it is. Like whenever you come across any farm, there is a particular kind of crop that is grown. Like for example, it may be sugar cane, it may be rice, it may be wheat, barley, or anything. Okay, so every crop will have its own crop coefficient. Okay, so crop coefficient will depend upon the stage of the maturity of the crop and what is the density with which the crop is being grown. So basically crop coefficient is defined for any given particular crop. Okay, so after that what we need to find out is to calculate what is the monthly consumptive use of that crop. Okay, so you can see that there are two equations over here. Et is the evapotranspiration. Okay, evapotranspiration is 2.54 times of k into f. K is representing the crop coefficient, f is representing the consumptive use of that particular period. Okay, any given duration. Okay, now how do we calculate f? F is calculated by summation of pH into TF divided by 100. Okay, now let us look into what is pH is. pH is the monthly percentage of annual daytime hours, depends on the latitude of the place. Okay, so this is a value which is given for one particular month, monthly percentage of annual daytime hours. So what it gives is the average of the percentage of daytime hours in for a given month. It means what? Like for example, every day they'll account the daytime hours. Okay, like for example, there is night hours are there, then there are daytime hours are there. So daytime hours are cumulated, and that is given for one month. Okay, and then the percentage is taken for an annual period. Okay, like this there is a chart that will be given to you. Based on that you can find out for January, February, or any given month what will be the percentage of daytime hours for that year will be given to you. Okay, once you get the pH value, here pH is representing monthly percentage of annual daytime hours. Okay, you remember this. So this value of daytime hours will change from latitude to latitude. Okay, it will not remain same for all the places, right? So for any given place there will be a percentage of daytime hours for any given month. Okay, so we have to get that data. So after that what we need to take is the monthly temperature. What is the temperature during that time? Okay, we know how much is the sunshine hour or daytime hours, then we need to find out what will be the temperature, mean temperature of that particular month. Like for example, if I'm calculating for January, I'll determine what is the percentage of daytime hours for January. Then I'll find out what is the mean temperature, what is the average temperature for that particular period, which is January, right? So once I get to know both of them, so what I do is I'll use this equation called F. F is giving me the sum of monthly consumptive use factors for that period. Okay, so pH is monthly percentage annual daytime hours multiplied by temperature, mean monthly temperature, divided by 100. Like this you calculated for January. Okay, like any crop will have its own duration. Okay, like for example, a base period will be there, then there is a maturity period is there. Now any crop that like from seeding to harvesting is called as base period, right? So some crops are grown for 4 months, some crops are grown for 9 months, 6 months and a year. Okay, I'll give a brief example of this. Like for example, if you go for small crops like grapes or any horticulture crops, they'll be their growth period will be less than 2 months or 3 months. If you go for sugarcane, rice or any other crops, they will be of more than one year or something, near to 1 year or something like that, right? So every crop will have its own base period or the duration with which the crop grows. Okay, growth of any crop. Now we need to study for that given crop how many months are required to get the complete harvest. Okay, from sowing period to harvesting period, right? So we need to find out that, like for example, I'm giving you, if there is a crop which is grown for 4 months like January, February, March and April, so you need to take the data of pH and TF, okay, for all the 4 months, and we need to take the sum of all of those. Okay, sum of pH into TF divided by 100, that will give you the F value. So this gives you the consumptive use of that particular duration. Okay, so once you get what is the F value, which is the consumptive use factors for that given period, which is for 4 months, next you will multiply with the crop coefficient called K, and if you multiply it by 2.54, it will give you ET. ET is the evapotranspiration for that given crop. Okay, so this ET is nothing but called potential evapotranspiration. This is not giving you actual evapotranspiration, this is giving you potential evapotranspiration, which means what? The maximum evapotranspiration that can take place from that particular zone during that period for that particular crop itself. Okay, so this is how the Bandy-Curdle method can be used. First, what you need to identify is what is the type of crop. From the type of crop you can identify what is the crop coefficient. Then you need to decide what is the base period of that particular crop. Then you need to find out how many months, like basically when you come to know that a particular crop is grown for 4 months or 6 months or 7 months, so for you have to get the data of monthly a monthly percentage of annual daytime hours. You need to find out the sunshine hours. Then you need to find out what is the temperature, mean temperature of all those months. So if you get all those data, you can be able to estimate what will be the potential evapotranspiration from that particular area. Okay, once you get to know the evapotranspiration is measured or it is calculated in terms of centimeter. And also you try to observe here, the mean monthly temperature is in terms of degree Fahrenheit. It is not in terms of degree Celsius, it is in terms of degree Fahrenheit. Okay, right. So this is how we can use the Bandy-Curdle formula. Next thing is we'll quickly solve a numerical problem. I have already solved a numerical problem which is given in one of the question paper. I'll quickly read the problem that is given to you. For the data given in table below, determine the evapotranspiration. The crop factor may be taken as 0.8. So crop factor, which means K value, is 0.8. Okay, then this crop is grown for 4 months, which is November, December, January and February. And in the question itself they are given you what is the mean temperature. Okay, what is the mean monthly temperature of November? It is 18, for December it is 15, January it is 13.5, February it is 14.5. okay, mean monthly percentage of daytime hour of the year. Okay, now you can see that 7.2% for November, 7.15% for December, January 7.3%, February 7.1%. So once you get the data of pH and T and you know what is crop coefficient, we can determine how much is the evapotranspiration. I'll just show you the Excel sheet in which I have solved. You can see this is the Excel sheet in which I have solved the what do you say, like evapotranspiration. So I'll multiply these two here. This equation here, you can see this value is calculated by multiplying 18 into 7.2. okay. Similarly for December, January, February, everything is calculated. Now this has been summed up here. Okay, so in this equation over here, I have calculated what is the value of f. F is calculated by taking the sum of this and dividing it by 100. Okay, so from this I calculated how much is f value which is consumed to use for this 4 months, which is 4.3835. okay, so this is the value I get. Once I get this value, it is representing me the f value. Okay, I have solved for f, I have to solve for ET now. Now to solve for ET, what I have to do, I have to multiply the crop coefficient here. So this value which I got is by multiplying the f with 2.454 and also the crop coefficient which was given to you in the question, which is 0.8. okay, after multiplying 2.54 crop coefficient and f which is calculated here, I got to know how much is potential evapotranspiration, which is ET. okay, now what you do is that you can also solve this on your own. Take this problem, note it down, and then you try to solve this. This is how we can use the this is how we can solve the evapotranspiration. okay, right. So once we understood evapotranspiration, I had already given you a brief introduction of infiltration. What is infiltration rate, what is the infiltration capacity, and all of those. Now we'll directly look into some of the methods through which we can calculate the infiltration. okay, now going with infiltration, there are several methods in which we can calculate the infiltration. Now look into this. There are different types of infiltrometers. Infiltrometers means what? Any given device which can calculate or which can determine the infiltration from a particular area. okay, now there are two methods. One is by flooding type method. Flooding type method, in this what we do is that on any given surface we pour the water, and then we watch how much water gets infiltrated into the soil. okay, so this is called flooding method. I'll tell you what are the scenario in which we flood any given region. okay, so there are two types of flooding type infiltrometers. One is single tube flooding, the other one is double tube flooding. okay, so we'll see that later. And there are other methods in which we can calculate the infiltration, and which is more advanced and which gives you more precise value of infiltration, which is the second type is called sprinkling type infiltrometers, or it can be also called as rain simulator. Usually infiltration takes place when there is a rainfall, right? So you try to imagine, we are not interested in knowing how much water gets infiltrated from a pond or from any like detention bodies. We are interested to find out how much is the infiltration that is taking place in a irrigation area or in a agricultural area. Now with that perspective, you have to generate an artificial rainfall kind of a system. okay, so what we need to do is that we have to use a given zone or an area. There we need to create an artificial sprinkle. okay, so as you can see, the sprinkler can be artificial way of creating a rainfall, right? So these are some of the methods through which we can create this rain simulation in Infiltrometer. The first one is needle drip system, standby pipes, sprinkler nozzles, and rotating boom. Okay, so these are the methods. Anyway, in your syllabus they have not told you to study all of these methods, but for your information I'm telling you these are some of the methods are there. In this, what they do is that they'll create an artificial rain by using sprinklers, and then they determine how much is the infiltration that is taking place on that given area. Okay, now let us get into this double tube or double ring infiltrometer. In some of the textbook they'll give it as a double ring infiltrometer, and this is a type of flooding in nature. So let me explain you what is flooding in nature. As you can see in this figure, these are the two jars I have. These are the two rings. Okay, they are penetrated into the soil. Okay, as you can see, this is the ground level we have. Now this is the total depth of that two rings. Two rings will be there, two concentric rings, as you can see in this 3D figure. So this is one ring, outer ring. This is the inner ring. Outer ring will be of 60 centimeter, inner ring will be of 30 centimeter, and then there is a rod. This rod is representing a scale. okay, where you can measure the depth of water in that ring. Okay, so what happens here is we penetrate these two rings in the soil, in the earth. Okay, so there are some observations that you have to do. You have to make sure that these rings should penetrate up to 15 centimeter beneath the earth surface, and earth surface should not be disturbed in nature. You understand, right, what is disturbed and undisturbed soil? A disturbed soil is one which we have excavated, or which we have man-made, man has intervened in the structure of that soil. Okay, so he should not in any means he should not disturb that particular soil, right? I hope you remember in soil mechanics also there is an experiment called core cutter. In core cutter, what you do is that it is called an undisturbed soil. You penetrate the core into the soil and you take that undisturbed soil, right? So here also we'll do the same thing. We have to select a place such that it should not be disturbed in nature. That soil should not be disturbed in nature. It should be naturally available. Okay, so in that area we penetrate these two rings, and this ring should be penetrated up to 15 centimeter from the top surface of the soil. Okay, right. So then we pour the water in both the rings. It is not that we pour in one side, we pour the water in both the rings. Then as in case of rain gauge stations, what used to happen, we used to collect the rainfall, okay, right, and then we used to measure how much is the depth of water collected, right? So here opposite thing will happen. Okay, so first we'll pour all the water, then we'll note down how much the water is getting penetrated, or how much is the water getting seeped out, or how much the water is getting infiltrated, right? So when you pour the water in both the rings, what happens is, as you can see, the direction of flow of water, right? So the water that is there in the outer ring will flow in the lateral direction, okay, in the horizontal directions like this, and this enables the water which is inside the inside ring, which is in the 30 centimeter diameter ring. The water in the 30 centimeter ring will flow in the vertical direction. So we are interested, if you are calculating for infiltration, we are interested to know how much is the water that is penetrated in the vertical direction. We are not interested in knowing how much water is flowing in the lateral direction, right? So that's how we calculate. As you can see, this rod is like a scale, which is a altitude measuring instrument. So using this we can measure how much is the depth of water that is getting infiltrated. Okay, now with respect to duration, we keep on noting the value of infiltration. Like for example, initially what we'll do is, like for a small period of 2 minutes, 3 minutes, we'll take the observation. Then we keep on taking the observation for every 5 minutes, 10 minutes, 20 minutes, like that. And then we'll see every time the time increases. As the time increases, the water will be penetrating into the soil, right? So we are noting all of that depth values. Okay, so from that you will get a graph. Okay, I'll show you what is that graph we'll get, but this is how we can find out the infiltration. Now assume for any given soil, in 5 hours around 10 centimeter water has been penetrated, or it is getting infiltrated. So it gives you how much is the infiltration that is taking place in a 5-hour duration, right? So if there is a 5-hour duration of rainfall, 10 centimeter of water will get penetrated. So this is what our assumption of this infiltrometer. Okay, I hope this is very much clear. So in future we are going to understand or study or try to find out the infiltration values, infiltration rate and infiltration capacity from the infiltrometers. Okay, anyhow, we'll solve the problem of that. Okay, I hope this is very much clear to you, what infiltrometers are and what is double ring infiltrometer is. Okay, all right. So next thing is Horton's equation. Horton is a scientist who has given us equation to calculate the infiltration rate. And I have already explained you what is infiltration rate. It is the rate of water that is infiltrating at any given time, right? So infiltration, if you want to calculate how much is the infiltration for any duration, so what we need to do is that we need to use this equation called as Ft is equals to Fc plus of F0 minus Fc into e raised to kT. Okay, some of the textbooks, they might have mentioned FT as FP. Okay, see here in this diagram that I inserted in the PPT, it is represented as FP. Okay, do not get confused. What is FP and FTR? Both are same. Okay, I have written FT because you are calculating infiltration for any given time, so that's why I written it as FT. In some of the textbook, they might have represented it as FP. Okay, do not get confused. Both are same. Okay, anyhow, you can see that FC, F0 are there, then e raised to minus KT is there. So to better understand this equation, what we can do is that first we need to understand what is infiltration and how it takes naturally. Okay, now let us look into this figure. Okay, this figure you can see. Okay, and now you already know what is hyetograph is. Hyetograph, which I had explained in rainfall. Okay, while representation of rainfall, there was mass curve and hyetograph. I had explained you what is the importance of hyetograph, and I told you that the same hyetograph will be and we'll understand the same hyetograph with respect to application in infiltration and in runoff also. When we are solving for runoff, there also I'll use the hyetograph, and in understanding the infiltration curve also we are using the hyetograph. Okay, right. Now look into these bars. These bars are representing the intensity of rainfall. You can assume that the intensity of rainfall is given in terms of centimeter per hour or mm per hour. Okay, so in this given table or in this given chart, the infiltration rate is there, which is written in terms of centimeter per hour. It means what? This hyetograph is also in terms of centimeter per hour itself. Okay, right. So for any given region, you can develop such infiltration curves. Okay, can you see this infiltration curve? Here it is represented. This is infiltration curve and this is your hyetograph. Bars are your hyetograph and this curve is your infiltration capacity curve. Now let us understand this infiltration curve in a more practical way or in a more natural condition, how the infiltration takes place. Now assume that before the storm period, okay, like every storm or every rainfall has got some period, right? 5-hour duration period, 6-hour duration period, 8-hour duration period, like this. So rainfall happens for some given particular hours, right? Now initially assume that there was no rainfall at all. Your land is completely dry, your vegetation is completely dry, and entire region is completely dry, and there is no water at all on the surface of the earth. So in that period, what happens? Initially, whenever the rainfall starts, you can see that the infiltration rate is very high. Why the infiltration rate is very high? Because there is no moisture in the soil. There is no moisture in the soil so that the water can be taken up by the plants. So that's how the infiltration value is really high when in the initial periods of the rainfall. Okay, once the voids of the soil are filled with water, once the moisture starts accumulating in the soil, once all the water required for the plants are being covered up or it is taken up, and what happens next is that the infiltration rates keeps on reducing. Okay, why it is reducing? Because during this period all the voids are getting filled up. So initially it will take a lot of water, the earth or the soil will take a lot of water. So after some point of time, when the voids are getting filled up, the infiltration rates keeps on reducing. Okay, right. Now once we understood this reduction in the infiltration rate from initial infiltration to constant rate of infiltration, now we will try to understand how he has derived this equation. Okay, as you can see this equation here, Ft is representing the infiltration rate at any given time. Like for example, somewhere here I want to find out how much is the rate of infiltration. Okay, so if you want to determine how much is the rate of infiltration over here, we need to first determine what is F0. F0 is representing the initial rate of infiltration, Fc is representing the constant rate of infiltration. Okay, so from this graph you can understand where is initial infiltration. This is your initial infiltration, this is your constant rate of infiltration. Now I told you that this will be a non-linear curve. Okay, if this is a non-linear curve, I can use this exponential term. Okay, e raised to minus kt. Now why am I using minus term? Minus term is representing the reduction in the infiltration rate. If it was positive, it would have represented the increase in the infiltration rate. So obviously the infiltration rate is reducing, that's why he has given us e raised to minus kt. T is representing a time. Like for example, I can substitute what is the time in here. If I know what is f0 and fc, I can calculate how much is ft value. I can calculate how much is the infiltration rate at any given time. Okay, so you have to substitute t in terms of hours, substitute fc, f0, and you will calculate how much is ft. Like this we can generate the infiltration curves for any given region. Okay, we can calculate them, all these parameters like k, f0 and fc for any given region, and then from that we can determine what will be the infiltration capacity curve for any given crop type or area or any type of soil. Okay, so this is what Horton has given us, but the question that comes in your mind is that how to determine these values called fc, f0, k and all of these values. Okay, so I'll explain this while solving the problems. Okay, I hope this is very much clear to you. This equation is representing fc plus of f0 minus fc e raised to k t. Okay, now just to give a brief example of how this behaves, like fc is the constant rate of infiltration, okay, from here to here. Okay, now if I want to determine how much, like for example somewhere here I want to determine how much is the rate of infiltration, we already know this here from here to here it will be fc. I have to calculate an extra altitude from here to here. So to calculating this will be based on this term. What is this term? f0 minus fc e raised to minus kt is giving you altitude from here to here. If I add the altitude from here to here plus of fc will give you the total ft. Okay, anyhow while I am solving the problem also I'll explain it again. Okay, now this k is basically depends on the type of soil and vegetation that we have. Okay, now let us look into the solution, how to determine this k value and ft and fc value. It can be calculated by converting this nonlinear curve. This is basically a nonlinear curve. We have to convert into linear curve. If I convert this nonlinear curve into linear curve, I could be able to define what is k value, f0 and fc value. Okay, anyhow I am going to solve the problem on this, but before that what we'll do is we'll quickly look into this equation that has been solved to you. Okay, now see here, this is ft was there. Okay, ft I send it to this side, it will become ft minus fc. So here ft minus fc is equals to f0 minus fc into e raised to minus kt. Now this is a non-linear equation itself. Now to convert this into a linear equation, what I'll do is I'll apply the log on both the side. If I apply log on both the side, it will become log of ft minus fc is equals to log of f0 minus fc minus of k into t. Okay, this is what the equation will be converted to. Okay, now from this I am supposed to determine what is k value, fc and f0. Okay, by using this equation. So when I am solving the problem, I'll explain you in detail of how to solve these values. Okay, I hope you understand the way in which I converted this linear curve to non-linear curve. Now quickly you see whether it is linear curve or not. How to see it as linear curve? This is y. Okay, this is the change that is going to happen because of t. Okay, so log of ft minus fc should be calculated, and for particular time. Okay, t is your variation. Okay, as t changes, log of ft minus fc will change. Now here log of f0 minus fc, you know f0 is constant, which is initial rate of infiltration. fc is also constant rate of infiltration. So log of f0 minus fc is your constant, minus k is your m. Okay, I hope you remember what is your linear equation is. Y is equals to mx plus c. M is represented by m is represented by minus k, x is represented by t, y is represented by log of ft minus fc, and constant is represented by log of f0 minus fc. Okay, this is how we can solve the Horton's equation. Okay, right, thank you.